Welcome everyone. There's a few seats down the front if you're still looking for seats. Come on down. Just before we get started, someone dropped a ring over in the atrium. Is anyone missing a ring? No? Okay. Well, it'll be up here if you realise it's yours later. All right, we'll just give people one more minute to get settled. There's a few seats down the front if you're looking for a seat. Okay, everyone. Well, welcome. Thank you so much for being here. On behalf of the Moyal Medal Committee, that's myself, Associate Professor Maurizio Maniguera, Associate Professor Richard Garner, Professor Dave Spence, who's not here today, Professor Dave Coutts, and all from the School of Mathematical and Physical Sciences, we welcome you to the 2025 lecture and presentation of the Moyal Medal to Professor Tamara Davis from the University of Queensland. My name is Petra Graham. I'm the chair of the Moyal Medal Committee this year and an Associate Professor of Statistics in the School of Mathematical and Physical Sciences. A special welcome to Professor Sam Muller, who's the Executive Dean in the Faculty of Science and Engineering, and to all of you in the room. We're very glad you're with us today. So I'd like to begin with an acknowledgement of country, and I'm sure you saw the beautiful Macquarie lands that you walked around as you came through here today. And so I'd like to acknowledge the Wallumattagal clan of the Darug Nation, the traditional owners of Macquarie University land, a place where knowledge has been shared and continues to be shared for thousands of years. We pay our respects to elders past and present. So next I'd like to turn to Joe Moyal, whose achievements and legacy we're here to continuously celebrate through the Moyal Medal. He was born in Jerusalem on the 1st of October 1910 and died in Canberra on the 22nd of May 1998. Joe Moyal was one of Australia's most remarkable scientists. His insight into the interaction between mathematics, physics and statistics led him to make contributions to these disciplines which have had far-reaching ramifications in all three fields. The Moyal formalism, which he introduced in 1949, is being developed today in physics as the Moyal quantum mechanics. Born and raised in Palestine under the British Mandate in 1910, he went to France to study, then work in electrical engineering. He moved to Cambridge to study mathematics, then returned to Paris to study statistics and theoretical physics. His academic career started after the Second World War as a mathematical physicist in Belfast and then as a statistician in Manchester. At this time, he made fundamental contributions to both fields, including the Moyal bracket into physics and developing the foundations of stochastic processes. Moyal came to Australia in 1958 and worked for 6 years in the Department of Statistics at the Australian National University in Canberra, making fundamental contributions to the theory of population processes, enabling researchers to track population size as well as the characteristics of individuals. He extended his work at the Argonne National Laboratory near Chicago, where he worked from 1964 to 1973 on the peaceful uses of nuclear energy. He returned to Australia to spend the next 5 years as a Professor of Mathematics here at Macquarie University. Following his retirement, he went back to Canberra, where he maintained his interest in the fundamental questions of science. In 1997, the Australian National University conferred on him the honorary degree of Doctor of Science, stating that he is one of a diminishing breed of mathematical scientists working in a broad range of fields, in each of which he has made fundamental advances. In 1963, Joe married the distinguished historian of science, Anne Moyal. After Joe's demise in 1998, Anne wrote his biography, Maverick Mathematician. Anne attended almost all of these Moyal lectures, delivered annually since 2000 until her passing in 2019. The recipient of the Moyal Medal will have made distinguished contributions to research in mathematics, physics, or statistics. It is awarded annually on a rotating basis in these disciplines. And now I'd like to invite Professor Dave Coutts, the head of the School of Mathematical and Physical Sciences, to come up and say a few words about Tamara. Thank you.
Thank you very much. So it gives me great pleasure today to introduce the 2025 Moyal Medal winner, Professor Tamara Davis, who is receiving this award in recognition for her outstanding contributions to astrophysics and cosmology. So Professor Davis is a world-leading astrophysicist at the University of Queensland School of Mathematics and Physics, where she studies the mysterious dark energy that is accelerating the expansion of the universe. She completed her PhD at the University of New South Wales on theoretical cosmology and black holes, and subsequently had postdoctoral fellowships at ANU and the University of Copenhagen before moving to the University of Queensland in 2008. She was the dark theme leader within the ARC Centre of Excellence for All-Sky Astrophysics, and is now the Deputy Director of AusGrav, that's the ARC Centre of Excellence for Gravitational Wave Discovery. And she also leads the Australian Dark Energy Survey. So in addition to the 2025 Moyal Medal that we're awarding her today, Professor Davis has been recognised with many other prestigious awards. And just some of these include the Astronomical Society of Australia's Louise Webster Medal, a L'Oreal Women in Science Fellowship, the Australian Institute of Physics Women in Physics Lectureship, the Australian Academy of Science Nancy Mills Medal. She won an Australian Research Council Laureate Fellowship. In 2022, she was appointed a member of the Order of Australia for significant service to astrophysical science, to education, and to young astronomers. And this year, she's been elected a Fellow of the Australian Academy of Science. So that's a very, very impressive CV. So we're very privileged to have her with us today to present the Moyal Lecture, and I'd now like to invite our Executive Dean, Professor Samuel Muller, to make the official presentation of the 2025 Moyal Medal to Professor Davis. So.
Good evening, everyone, and it's exciting that you are all here tonight to celebrate the special achievements of Tanya. But before we go, the effort of Tamara. But before we go there, just two additional facts. Firstly, I welcome family of her who came all the way from Alexandria, Sydney, not overseas, to celebrate with you. And the second thing is I looked up her website, and it said on her website, and you write about your passion for sport, and that sport teaches you so much, and particularly ultimate frisbee. And I didn't know much about ultimate frisbee, so I had to look up what is so special about ultimate frisbee. It's one of those sports where there is no referee, and it's all about fair play, and people call their own fouls. And I was thinking how beautiful that relates to how the process is selecting a Moyal Medal winner, because it is peers who look around, look at their peers and identify those who are most worthy. And the main criteria first is academic excellence, and that is why you received the medal. But it is much more than this. we look for someone who is a bit more rounded, more complete, but also an excellent citizen. And Tamara, you tick all those boxes, and so it is my very great privilege to award to you on behalf of the Moyal family and the Moyal Medal Selection Committee, the 2025 Moyal Medal.
Thank you, Sam and David. And now we'd like to invite Professor Tamara Davis to come and give her Moyal Medal lecture.
Thank you so much. Thanks to Macquarie, thanks for all of those amazing introductions. I feel like they've talked me up a little bit too much, and now I have a little bit too much to live up to, but hopefully I can do that. And so just quickly getting those slides up. I think it's this one. Isn't it? Oh, there. Yeah, sweet. Yeah, so thanks so much for the honour of being given the Moyal Medal. It really is a very special thing to be recognised by your peers in this way. And it's very cool that you called out the sport as well, because I've learnt so much from playing sport that translates into managing people and doing things as a group and collectively that translates beautifully into working as an academic as well, or into many fields. So before I kick off properly, I'd like to also acknowledge the traditional owners of the lands on which we meet. And I wanted to pull up one part of the astronomy from the Aboriginal people, and that's the emu in the sky. I hope you're all familiar with the emu in the sky. One of the reasons I love the emu is that I was brought up in the tradition of making constellations out of the bright points in the sky, like we see Orion and Orion's belt and stuff like that. But this particular constellation is made up of the dark patches in the sky. You've got the Milky Way going across the sky, and it's the dust clouds that are obscuring the background that give you the dark patches. And when I heard that, it blew my mind. I was like, yes, this is a completely opposite way of looking at things. And considering that I study the dark side of the universe, dark matter and dark energy, this seems particularly poignant to me as well. Yes, so as I said, thank you. It's a real honour to be given this medal. Thanks to Macquarie University and the Moyal family for the medal here. I really enjoyed reading up about Jose Moyal while preparing this talk. And so I'll chuck up his Moyal bracket, which is one of the things that he's famous for. And for those, the kids, my family and stuff that are in the back, and the other kids in the audience, I don't know if you knew you could do maths with stars, but there's stars in there. And I'm not going to go through what all of this exactly means, but it's a useful thing for quantum mechanics. And this F times G sort of thing and minus G times F thing is actually important when you have things that don't commute. And now, what is commutation? I thought I'd give you at least that much for Moyal's sake. Now, commutation is if you can do things in like 2 times 3 is 6, 3 times 2 is 6, they're both the same. It doesn't matter which way around you put the 2 and the 3. But there are some things that it does matter which way around you do it. For example, if I walk 3 meters and then turn 90 degrees, that's different than if I turn 90 degrees and walk 3 meters, right? Those two will give you different results. And how far you are from the destination is a thing that this kind of maths can help you know. Or another thing that doesn't commute, I took this from Gary Larson, is you should put your socks on before your shoes in general. It doesn't work the other way around. It was actually pants there before, first pants, then shoes, but I changed it to socks because that seemed more natural. Anyway, also thanks to my family, Mum and Dad are in the back there. They were really supportive of everything I did growing up, whether it was playing ridiculous amounts of sport or reading my books and studying. Also wanted to give a shout out to my niece and nephew in the back there, Liz and Luca, who have come along. They don't get to come and hear me speak science very often, so it's great to have you. Okay, so to the science, kicking off with our place in the universe. So if you've heard the Hitchhiker's Guide to the Galaxy, you've read the intro to that space, it's big, really big. Here's a picture of the Earth from space. It's like you can see the space station in the foreground there and everything. Zooming out a little bit further, this is a really famous image. This is Earthrise. So this was an image taken by the Apollo astronauts when they were orbiting the moon. And this is actually one of the first pictures humankind ever took of the Earth where you can see the phase, like you can only see the light shining on part of it. We got far enough away to be able to see the Earth in this type of image. So it apparently was quite instrumental in kicking off some environmental movements and that kind of thing. When you actually see our Earth floating in space like that, it gives you a new perspective that until this point humanity had never actually seen. Let me keep this as well. Now this next picture is also a picture of Earth. It might not look like the Earth that you recognize though. Can you see it? Yeah, and that's because Saturn's in the way. That's Earth. Can you see Earth? That little tiny dot. So this was taken by the Cassini spacecraft as it was flying out past Saturn, and they turned it around and took a picture of Earth through Saturn's rings. So that's a pretty cool picture. That's what we look like if you were basically hanging out around Saturn's orbit. And this is the most distant picture of the Earth ever taken. This was taken by the Voyager spacecraft as at one of the last times it could turn around and take actual pictures. Can you see Earth? Yeah? Is that little dot there? And if you go and have a look at this Carl Sagan quote, it's much longer than this, but he goes on, like, look again at that dot, that's here, that's home, that's us on it. Everyone you love, everyone you know, everyone you've ever heard of, every human being who ever was lived out their lives. And he goes on to say things like, you know, every hero and conqueror, every slave, etc. And I think one of the important things we learn by doing astronomy is that sort of perspective that you bring looking back at our place on the Earth. And when you think about our planet, just how precious it is sitting in this vastness of space around it. Nice. But this is still super local. This is still our own solar system. If we look a bit further away, this is what our galaxy would look like if we were able to fly out of the plane of the galaxy. We're hanging out about 26,000 light years from the center in one of the spiral arms. And the Earth, interestingly, is oriented like this. This is not to scale, but we're oriented with the South Pole slightly pointing towards the center of the galaxy. And that's actually one of the reasons why we get such a spectacular Milky Way from the south of the galaxy, because if you're in the northern hemisphere, you're sort of pointed out towards the outskirts of that disk, whereas if you're in the southern hemisphere, you're looking more towards the center, so you've got a lot more stars in the Milky Way that we see from the southern hemisphere. And this is a photo from Siding Spring Observatory. You can see the Magellanic Clouds out in the corner here. These are our nearby galaxies that we're sucking into the Milky Way and gobbling up. And this is the galaxy, and where our galactic center is, with a black hole in the middle of it, would be about there. This is the Sky Mapper telescope at Siding Spring. But even looking at the galaxy is really local for the work that I do. I tend to go much further away. Now, hopefully many of you are also familiar with this image. Can anyone tell me what it is? Yell it out if you know. 2DF. Not 2DF, but not even James Webb. This one was from Hubble. I heard someone say deep field over here. Yeah, the Hubble Ultra Deep Field, this one is. This is a picture of an empty patch of sky. This is what you get if you find a piece of sky that doesn't have any stars, doesn't have anything that you can see in there, but you take the Hubble Space Telescope and you point it at that patch of sky and keep the shutter open for 11 days. You see this amazing array of galaxies that were simply just too faint to see before. So it's this super long exposure. Now, every basic dot there is a galaxy. This one down here is a star. You can see the typical crosshairs, and there's one up the top here. Yeah, that's a star, but I think every other dot here is a galaxy. That means they each contain hundreds of billions of stars. And the most distant ones in this image emitted the light that we're seeing about 13 billion years ago. So we're looking really deep into the past when you look at images like this. And whoever said JWST, this is the one that from the James Webb Space Telescope as well, where you can see all sorts of cool things. JWST has different optics, so you get these multi-pointed stars, and you also have these like cool lensed features where the galaxies are being warped by the mass in the foreground that you can see. So these are absolutely beautiful images. Now I've got a little animation here, which is a zoom out from a Hubble Space Telescope image, similar to the deep field. And as you zoom out, it's superimposed on other images from other telescopes with wider fields of view. And as you zoom out, and you zoom out, and you zoom out, eventually you get to the constellations that you might recognize. Was that cool? Anyone want to see that again? All right, let's do it again. So I feel like this gives you a much more visceral feeling for just how far you're looking when you look at these images. It's just, the zoom in that we're getting with these telescopes is absolutely spectacular. And it's thanks to that amazing ability of our modern telescopes that we've learnt some really cool but weird things about the universe. Now, two of those things are the things that I study. So dark energy and dark matter. Now, dark matter is probably a particle. It clumps, it pulls, it literally binds our galaxy together. And dark energy, on the other hand, it pushes. It, for some reason, is accelerating galaxies away from each other. So it's making the whole expansion of the universe speed up. Now, we have heaps of evidence for each of these, and I'm going to go into a little bit of the evidence primarily for dark energy and some of the cool stuff that we've found out about dark energy in the last few years. But because we've started going into the depths of space, I thought I'd take us back home and go to ground us with a picture of a tree. There's a reason for this, though, is because the dark energy and dark matter, we can't actually see them. They're dark, they don't glow, they don't emit light. The reason that we know they're there is because we see how they make things move. So the spin of a galaxy tells us that it's spinning too fast and that dark matter something has to be holding it together. And I liken it to when I look outside and I see the leaves of a tree blowing around in the wind. I can tell that something's moving them. I can tell that there's wind there, but I can't see the air, right? And so similarly, we're seeing the galaxies in the universe being blown around by something. They're being influenced. They're being pulled by something that we can't see. But their movement is what's telling us that there's something there to be seen, to be discovered. And so that's what we're trying to figure out. So I'm going to give you a little bit of an adventure going through the discovery of the expansion of the universe and the cool acceleration stuff that we're studying these days, and give you a bit of insight into the cool experiments and equipment that we get to use to be able to try and probe these mysteries. Are you ready? Yeah, let's go. Okay, about 100 years ago, the discovery of the expansion of the universe. The big question is, how do you convert an image like this that's two-dimensional into a 3D map? The challenge is, it's really hard to tell whether some of these dots are really faint things nearby or really bright things that are really far away. So how do you know that? Well, the first, really, you can use parallax, like using your two eyes, but we don't have much parallax here on Earth. So we need something else. And in the early 1900s, Henrietta Swan Leavitt was responsible for discovering this cool feature of Cepheid variable stars. There was this particular type of star that oscillates in brightness. And the faster it oscillates, the brighter it is. And we can see these in our own galaxy and measure that. And that's really handy because that makes it a standard candle. It means that by measuring how bright it appears, you can tell how far it is away. Does that make sense? So if you know how bright something actually is, and it's literally like if I grabbed a candle and I came and held it up in front of your face, and then I took the same candle 100 meters down the road, in a completely dark night, you can make a pretty decent guess of how far I was away because you know how bright candles are. That's basically what we're doing. So now we had something of known brightness. And we combine that with the spectra. So we have the rainbow of light that we get from the galaxies. And if something's moving away from you, the light gets pushed to the red end of the spectrum. It's similar to the Doppler shift that you hear in sound. So if you might be familiar with the race car zipping past and it goes, right? It's the high pitched on the way to you and low pitched on the way away from you. And that's the sound waves compressing and stretching as they go towards and away from you. Well, the same thing happens with light. If something's going away, it's moving fast, so the wavelengths get stretched, and that means it gets redder, because red light has a longer wavelength than blue light. And we're able to measure the fingerprint of lines in these galaxies and tell how fast they're moving away. This is Vesto Slipher doing some of the observations that were used by a few people to do this. So in the late 1920s, a guy called Lemaitre and another guy called Hubble. This is Hubble here. He's doing two things that we never do at a telescope these days. Can you see what they are? Smoking and looking through the eyepiece. Yeah, we use digital cameras now. We don't have to freeze our butts off in the cold telescope rooms anymore. But he made this plot, which is these days pretty crappy data, but at the time revolutionary. Velocity on the vertical axis and distance on the horizontal axis. And you see, even with this sort of crappy data, that roughly the things that are further away are moving faster. And this was the discovery that the universe is expanding. Now, from then, it was hot on the heels of the discovery that the universe is expanding, that we saw dark matter, or some hint of it. And that was this guy here, Fritz Zwicky, wrote the first paper on it. Expansion, the papers were published in 1927 and 29, and 1933, first paper on dark matter. So this basically, the existence of dark matter was sort of blindingly obvious. The way that he did it was, once we knew that these little spiral things that we were seeing in the sky were actually galaxies, not just clouds of spiral gas nearby, but whole galaxies far away, he measured them in how they move in clusters. So you get these clusters of galaxies, and they orbit each other. And you could sort of make an approximation of how heavy the galaxies were, like what mass was in them, by seeing what stars they contained. But when he measured how fast they're moving, they were moving way too fast for the amount of gravity that you would expect from that mass to be pulling them together. The cluster should just like zoom around, the galaxies should just fly away from each other if they're moving this fast. So he speculated that there's a whole bunch of dark matter out there that we just can't see. And the idea at the time, well, maybe it's like dust, maybe it's just planets or something that has gravity, but it's not shining like a star. That didn't get a huge amount of attention, but the real clincher was Vera Rubin in the 1960s saw this kind of thing happening. So on the left is what you expect to happen with the rotation of galaxies. So there's lots of a really dense core, and when you're near something that's really dense, you've got to orbit fast, otherwise you're going to fall in, right? But on the outskirts of the galaxies, far away from that thing, you can go at a leisurely rate. You know, Pluto in our solar system, don't get into whether it's a planet or not, Pluto in the solar system is going at a pretty leisurely rate around the system, around the sun, because it's so far away, it doesn't have to go very fast to avoid falling in. And that's what we would expect to happen in our galaxy, and also in every galaxy that we see. But instead, we see what's on the right, where the outskirts of the galaxies are spinning really fast. And again, they're spinning faster than we should be able to explain, given the luminous matter that we can see, given the stars and gas. So this was a really strong hint that there was some dark matter out there. We have some heaps more evidence now, which I'll show a little bit more of later, but this was sort of the real kickoff. So even weirder, the discovery of dark energy. Ever since the 1920s, people had wondered whether this expansion that we're experiencing is going to stop and the universe is going to recollapse, or whether that expansion will go on forever. We thought that the galaxies should be pulling on each other, so they should be slowing down the expansion. But we didn't know whether they were pulling on it so hard that it would turn around and recollapse. So it's like the question of, if I jump off the ground here, gravity pulls me back to Earth. But if I was to jump at 11 kilometers per second, I might need to go to the gym a little bit, but if I could, if I jumped at 11 kilometers per second, then in the absence of a ceiling and air resistance, I would be able to escape Earth's gravity and never come back. So the question was, do the galaxies have the escape velocity from each other? Is it going to expand forever? To answer that question, we needed to have a better standard candle, a brighter one at least. And we discovered that in the 1990s with some people who realized that there's this particular type of exploding star called a type 1a supernova that always explodes to about the same brightness. So again, by measuring how bright it appears, we can tell how far it is away. But in contrast to those Cepheid variable stars we were looking at before, that one supernova can outshine the light from an entire galaxy for the time that it's bright. So one star exploding beats hundreds of billions of stars just shining. And that means that we can see these things really far away. And that's really key, because in astronomy, when you look at things far away, you're also looking back in time. So we can compare how fast the universe was expanding back then to how fast it's expanding now and see how that has changed. And so in the 1990s, these guys led 2 different teams to try to measure this. On the left is Brian Schmidt from the High Redshift Supernova team. On the right, Saul Perlmutter from the Supernova Cosmology Project. They were using the same telescope and but different observing patterns, and both teams came out approximately the same time with the same weird answer, that the galaxies are moving away from each other faster and faster. The expansion of the universe is speeding up. So something out there has some sort of anti-gravity. Something is making gravity push instead of pull. We don't know what it is. We give it the name dark energy. And this was discovered in 98, 99, and that was when I was about to start my PhD. And I was like, wow, that is what I want to study. That sounds fascinating. I want to know how to build those hoverboards that Marty McFly had in Back to the Future. I was told that I should have those by now. So if we can figure out how to make gravity push instead of pull, let's see what we can do. So this is pretty cool, and that's what I've spent my career studying. Now, if you can do this kind of thing and discover the acceleration of the expansion, here's those guys looking a bit more respectable. They're not pretending to fight at a conference anymore. They're getting Nobel Prizes instead. So that was sort of cool. I did get to go to Stockholm because I worked with all of these guys at some point, and I got to go to Stockholm during the Nobel Prize ceremonies. I didn't get to go to the cool part where you get to meet the king, but I got to go to the after parties and stuff, which was pretty cool. So anyway, so what could dark energy and dark matter be? Well, what's dark matter? Is it a new type of particle that is it part of our normal periodic table? Could it be black holes? Could it be modified gravity? Well, these days we're pretty sure it's a new type of particle, maybe with a little bit of a few black holes mixed in there as well. But it still could potentially be a modification to gravity, but we think it's probably a type of particle. What about dark energy? Well, the leading candidate is actually that it's the energy of the vacuum itself, the energy of empty space. Weirdly, quantum physics predicts that that empty space should never be perfectly empty, and it actually should contain a sort of repulsive force. And so, oh wow, done and dusted, that's it. That should be the solution. But it also predicts, in a rough way, how much of this stuff should be, and that prediction is 120 orders of magnitude wrong, which that's 1 with 120 zeros after it times the answer that we're meant to get. So that's a pretty bad match between prediction and observation. So it might be that is the cause, but we need a quantum theory of gravity to really explain it fully. So this is one of the reasons why dark energy and dark matter are so exciting, is it because we're really testing what the fundamental equations are that govern the physics of our universe and trying to understand how do we do better than what we currently have. So with that, this is what we're trying to do at the moment. We're trying to measure the dark energy and dark matter with more precision so that we can figure out what they are. And so one of the things that we've been doing is the Dark Energy Survey. This is the CTIO 4-meter telescope over in Chile. This is the beautiful camera that we've got on that thing. There's the size of the lens that we're working with. And with that, we can take images that look like this. This is one image. They're sort of pieced up because there's like lots of digital cameras because they tile the area because it's quite a large area. You can take something about 4 full moons across in one image. So that means it's really effective at surveying large patches of the sky. And across this whole image, we get a beautiful resolution. So it's just a super amazing instrument. And we had the privilege of working with the people who designed and built this. And we did a survey for 6 years, and we discovered and catalogued didn't necessarily discover all of them. We catalogued over 500 million galaxies, over 100 million stars, just accidentally found 700,000 asteroids in our solar system, and found tens of thousands of supernovae that we can use to map the universe. And we here in Australia, oh, sorry for that bright light, guys. Maybe I should put a light on me. But this is a really cool instrument that's on the Anglo-Australian telescope. It's called the 2-degree field instrument. And here at Macquarie, we've now got the AAO that is doing all sorts of amazing instrumentation projects. And this is one of the early ones from here. And this was a completely revolutionary instrument. It was built in the 1990s. And what you're watching is a robot place optical fibers at the positions of interesting objects in a picture that we took. So you take a picture of the sky and then you figure out where the interesting things are. You get the robot to put an optical fiber on each of them and then you tilt it so that each of those optical fibers accepts the light from an individual galaxy. So with this, because there's 400 fibers, you can measure 4 spectra of 400 galaxies at a time. It's a really efficient way of surveying the sky. And the spectra is like the rainbow of light. So you can measure this velocity of galaxies moving away really efficiently. And so it just so happens that these two are sister telescopes and they have the same field of view with these instruments. And so we could really efficiently follow up the telescope in Chile with spectra using our telescope here in Australia. And I'll give a shout out to Chris Lidman, who was really involved in getting this survey going. And after doing that for 5 years, we managed to look at something like this. So here, you have to imagine that you're in the center of this image looking outwards. You're looking along these sort of pencil beams. Every golden dot is a galaxy, and those sparkles that you see going off are supernovae going off in those galaxies that we detected with DECCAM. And they sort of disappear every once in a while because every 6 months we observe and then we turn off for a while the fields that we're looking at sort of go behind the sun. Sun can be really annoying when you're an astronomer, so we can't follow them continuously. But we found thousands of supernovae this way. And what we managed to do was, this is the original plot that Hubble did with the discovery of the expansion of the universe. So this was in the 1920s. This is the plot from the 1990s. It looks similar, but it just goes out much further. You can't even fit this plot on the bottom axis. It doesn't go down to 0 here. The Hubble plot was really off to the bottom here, and this is the plot that won the Nobel Prize for discovering the acceleration of the universe. And this is our plot. This is the plot as of last year, where we've measured out to here the most distant galaxies that we're looking at here emitted the light that we're seeing about 8 billion years ago. So to put that in perspective, who knows how old the Earth is? Yeah, it's about 4.5 billion years old. So the light that we're seeing here was emitted, and so it was emitted, it started moving over here, and then over here somewhere, there's a cloud of dust and gas that's collapsing. Eventually a star turns on, a disk forms there, little planets form in that disk, little creatures grow in the oceans of one of those and crawl out and learn to build telescopes. And meanwhile, this light keeps traveling, and the first thing that it's hit in that entire time is the mirror of our telescope. So it's really amazing to think of it when you see that way. I remember when I was a PhD student, no, I was probably a postdoc, and I first was at the Anglo-Australian telescope and accidentally saw a galaxy that was that far away, and I couldn't interpret what it was, and I asked my colleague, what am I looking at there? And he's like, oh, look at redshift 4, and I was like, oh, cool. And I was like, whoa, and then I realized we'd seen this galaxy that had emitted the light before the Earth had formed, and not only were we able to detect it with our telescopes, we were able to understand what it was. And I knew that it was a black hole that was gobbling up a lot of gas that was far away, which is what was making it shine so brightly. And I literally just pushed away from the desk and was like, whoa, that's cool. So yeah, I can get excited about these things. So the cool thing about this diagram here is that the number of exploding wee stars that we found at high distance, it increased by like a factor of 5 over anything that was known before. So 80% of the distant supernovae that have ever been measured at high distances were measured by our team. And obviously this is some of the team down at the bottom here. And so that was really revolutionary to the field. And I've said here that we discovered the acceleration of the universe. That's speaking very loosely. It's not exactly true. We discovered that the dark energy might be changing. But I phrased it this way partly because I thought it was cool. But does anyone know what the acceleration or the change of an acceleration is? So you've got the change in position is a velocity or a speed. Change in velocity is acceleration. Change in acceleration is jerk. So we discovered the jerk of the universe, you could say. Now, as I said, that's speaking loosely. What we've seen is that there's maybe some time variation to dark energy. So its properties might change with time. Oh, by the way, after jerk, it's sometimes given different names, but usually it's called snap, crackle, and pop as the next ones. Okay, so these are kind of some of the ways that we've discovered cool things about the universe. But one of the questions I get asked most is, where is the edge of the universe, and also where's the center? But one of the things that we're trying to do right now is essentially map the entire universe. So this is not the whole universe, this is a simulation, but this is the kind of filamentary structure that you get in the universe, where you've got, these are like dense spots are bright and voids are dark. And our observable universe would be a patch of something like this. We don't know whether the universe is infinite, but there is an edge to the universe that we can see that exists just because there's a finite time, a limited amount of time that light has been able to travel from the beginning of the universe till now. So there's a patch of the universe that we can see just because light hasn't been able to get to us from further away yet. And images like this, like when I go to the pub and say that I'm an astrophysicist, people are like, oh, wow. But then they're also like, well, what do you actually do? Do you like discover galaxies and stuff? And I'm like, well, discovering galaxies is actually super easy. You just take a telescope, you point it at a patch of sky that nobody has looked at for that long before, and you leave your shutter open for a long time and you see more galaxies. It's actually not that hard. But with images like this from JWST and the earlier one I showed from Hubble, that sort of quip is no longer true, because you're looking so far back in time with images like this. You're actually looking back to before galaxies had even existed. So you're looking back in time almost to the limit of what we can possibly hope to see with the universe. But this is not all the light that's out there. If you look a little bit further, you can see this. This is the cosmic microwave background. So this is actually a false color image. It's actually light that we've measured in microwaves. And you're seeing hot spots and cold spots that are actually fluctuations from back when the universe, the whole universe, was as hot as a star. So if you had been living back then, this is from about just under 400,000 years after the beginning of the universe. And if you had been living back just in the 300,000s of the thing, it would have been like living inside the surface of our sun, like inside the sun, but in a sun that goes in all directions as far as you can go. So we would have been fried to a crisp. It wouldn't have been very comfortable. But back then, sound waves were traveling all over the place really fast, because you had a really, really dense start to the universe. And it was only after the universe expanded enough that all this gas got more dilute and sound waves couldn't propagate anymore. But these hot spots and cold spots are compressions and rarefactions of a sound wave, massive sound wave that was going on in the early universe. And interestingly, these were predicted to exist. This is the best of evidence that we have that there was actually a Big Bang, because we can actually see the light that was left over from when the bang happened, basically. And I don't have too many plots in this talk, but this is such a beautiful plot that I have to put it up here. So this is, I'm not going to go into great detail of what it is, but basically what you're looking at is how strong the fluctuations are. So how high the hot and cold spots are compared to what their separation. And you see this wavy pattern, and that red line is basically what you would predict if you had the amount of dark matter that we saw in the spinning galaxies and the amount of dark energy that we saw accelerating the galaxies away with the supernovae. You would predict a red line that looks like this. And the blue dots are the data from the cosmic microwave background. And it's just, you can see it's quite a complex pattern. And that's basically, it's like it's like beats of a sound wave. And the data fits absolutely beautifully. Now, to show you, this is also evidence for dark energy and dark matter, because if I kept everything else the same and took the dark energy out of this theoretical model, then it would look like this. So it's really quite dramatically different if you don't have dark energy in there. And if you do the same and you take the dark matter out, it does even worse. So you can really see that this has nothing to do with spinning galaxies. It's a completely different source of data, right? But still, the same amount of dark matter that we expected from observing spinning galaxies can be seen in the data here. And we can do better because we can take that initial conditions that we can actually observe a few 100,000 years after the Big Bang, and we can put them in a computer and simulate them and move the movie forwards. And that's what you're looking at here. And this is how we create those sort of maps that I was showing before with the sort of dense spots and underdense spots. So this is a cluster of galaxies forming. Our Milky Way would be on the outskirts, like one of these little bubbles out the side or something like this. We're not in a big cluster. And so you can see over time, you go from quite smooth beginnings to quite clumpy formations later. So if I reverse the movie, you can see it's like pretty smooth there, and it rapidly forms into dense clusters, and you end up with clusters of galaxies going on in the future. And if you look at sort of what this is now a similar sort of map where this is a real simulation of most of the observable universe, and you've got voids and filaments and this sort of filamentary structure. And it gets out to the edge, it's getting more orange, and that's because they're actually saying what the universe looked like back then. Like if because we're getting the light and we're seeing the universe as it was in its infancy, and this is what it would look like back then. And so to finish off, I'm going to show you another measurement that we're doing with the dark energy spectroscopic instrument, which is another similar telescope to the ones I showed before, but it's on a telescope over in Kitt Peak, and we get to do this because of, thanks to the AAO actually, thanks to the instrumentation team that's now based here at Macquarie. A couple of us from Australia got access to this instrument over in Arizona because AAO did some of the instrument design studies to figure out how to make these optical fibers. Because just like that fiber positioner that I showed before, this is another fiber-fed spectrograph, but now we have, instead of one robot moving 400 fibers, we have 5,000 robots moving 5,000 fibers. And it's an amazing instrument. This is a movie that we actually made for a planetarium show, so you imagine this coming down from the top on a planetarium. But you zoom in, and this is like what the little robots look like, and they can move in. Each of these little like holes has a like little optical fiber sticking out of it, and they can move them around to capture the cool stuff that we see in the universe. And so what you do is you get an image, something like this. You decide which interesting objects that you want to put optical fibers on. You do that over the entire field because it's really big, and you measure the spectra of 5,000 optical fibers at a time. And this is a really cool instrument. So I told you about that, the one that we have been using here in Australia with the 400 fibers. When I first moved back to Australia to UQ in 2008, I did a survey there with a bunch of others where we took 5 years and we measured the biggest map of the distribution of galaxies in the universe that had existed at the time. And that was about 250,000 galaxies. With DESI, our record so far is we measured 138,000 galaxies in a night. So that's both really exciting and a tiny bit depressing that I took 5 years to do what we can do in a couple of nights now. But of course, we're building on the technology that was designed and developed here and taking it to our international stage this way. And this is the one of the maps. So this is no longer a simulation, this is actual data. And here, all of these dots in the background, the different colors are different types of galaxies we're looking at. And here you can see these filaments and structures that we see from the simulations of how we think gravity works. And we see them perfectly in the image, exactly how we expect them to be. And to give you a scale of this map, the light that was emitted from these galaxies was emitted about when the solar system formed. Again, we're at the center in here. The light that was emitted from there was emitted about half the age of the universe ago. And this was emitted about 11 billion years ago. So we're legitimately talking now about mapping every galaxy in the observable universe in the next sort of couple of decades using telescopes like this. And interestingly, that hint that we saw from supernovae that the dark energy might be changing its properties with time was also seen by this with our team using this a different method where you can take these galaxies and they're sort of like, there's a pattern in there that isn't random. And so we use that sort of like grid paper and use that as known distances to measure the expansion of the universe. And we're using this, using standard rulers instead of standard candles, we also saw the same type of variation that we saw with the supernovae. And that's getting really exciting. And so we released last year, and we got this New York Times headline saying a tantalizing hint that astronomers got dark energy all wrong. And I'm like, I hate those kind of headlines because no, we didn't get it all wrong. We were deliberately going out to try and measure its properties, and we found something interesting. So it doesn't look like it's as simple as we thought. It could still be a systematic error. It would still be something else we're not really sure yet. And so we still need to do more observations. We've finished the supernova ones for now, but we're starting a new project on a telescope called the Rubin Observatory over in Chile, after Vera Rubin, who saw those spinning galaxies for dark matter. And we're doing a project called the Legacy Survey of Space and Time, which will find a whole heap of supernovae there. Oh, here we are. There I got to visit it. And it's a super impressive instrument that's going to do an amazing job. And we'll end up with 500 petabytes of images over the course of its survey. So that's going to take a bit of disk space. And we're working on a whole bunch of other things as well, not only DES, which we've now finished, but we're doing some things like Foremost with more spectrographs, DESI, which I was just talking about, and of course the Square Kilometre Array pathfinders that's in Western Australia, and the Square Kilometre Array itself, which is being built at the moment. And I got the privilege to go out and see that very recently. And all of these we're using as new information to try and understand the universe. And it was mentioned at the beginning that I was Deputy Director of Ausgrav. Ausgrav's an awesome centre and we're trying to, instead of using supernovae to measure the expansion of the universe, we're trying to use gravitational waves, so these ripples in space themselves that you get when black holes collide or neutron stars collide. And they can potentially do an even better job than supernovae at tracing the expansion of the universe. Okay, so in my last couple of minutes, I did want to just talk about, I get excited for this stuff just because I think it's intrinsically cool and interesting, and I think it's amazing to try and understand the universe, but also because if we can understand the physics that governs these extreme things that are going on in the universe, maybe we can understand the physics here on Earth a little bit better. As I jokingly said hoverboards, but hey, if we can really understand what's causing the expansion of the universe to accelerate, maybe that is a new form of energy. Maybe that is a new kind of propulsion. Maybe that's a way to get off the surface of the planet that doesn't include a huge amount of fossil fuels or something. Who knows? We'll figure out, we don't really know that yet, but we're hoping that in exploring it, we can find some cool new physics. But while we're doing that, there's also a whole bunch of cool things that we spin off on the side. So I don't know if you heard, but there was some astronomers at the Parkes radio telescope who were trying to find black holes. But to do so, they needed to measure rapidly oscillating radio signals. And the code that they had wasn't good enough to do that at the times in the system. So they made this sort of some new software, and long story short, they never found the black holes, but they did invent a piece of software that now forms part of Wi-Fi, the 802.11 or whatever that you get in all of your Wi-Fi codes. CERN, famously, the way they do the particle accelerators, gave birth to the web there. One of my colleagues took some of the imaging techniques that we use in astronomy, and because when we do astronomy, you've got to adapt for the atmosphere if you're doing ground-based astronomy, and we often shoot a laser into the sky and measure how the atmosphere changes, so you can change the shape of the mirror that's detecting it 10 times a second or so to take into account the movement of the atmosphere and unblur the image. And she made an instrument that can do radiography that uses that technique. And instead of having one of these donuts that moves the machine around, you could actually spin the patient, making it much, much cheaper. But when you spin the patient, the organs and stuff move around. So she was using this adaptive optics system to refocus and change where the radiography hits, which made a much cheaper instrument. Some of my friends who are doing the gravitational wave detection, which uses lasers, are also using things like spinning off stuff that ends up being in self-driving cars, and things like precision gyroscopes for navigation where you don't use GPS and that kind of thing. So there's all sorts of things that you don't really think about when you're saying, oh, I'm trying to understand dark energy or trying to understand the universe, that accidentally come out of it. And I know there's a few kids in the room, so I thought I'd also talk about some of the places that physics can take you. This is one of my PhD students, Morag Scrimger, and she went and used her astrophysics degree to help a little tiny startup company called Square, which she worked at before it was famous as one of the original coders to try to figure out how to make the software in order to make these work. And now those are, you tap and pay with Square all the time, so that's a relatively successful company. And she's now doing medical research in Europe, where she's doing imaging of computer reconstruction of the internal workings of human bodies thanks to fancy imaging. Another one of my PhD students is Sam Hinton. This picture of him is actually from when he went on Survivor. There was a point where he was on Survivor and I was on ABC Catalyst, and we were airing at the same time on the night. So we had the ratings wars in our department. You can guess who won. But he's done a whole bunch of interesting things. When COVID hit, he stopped his PhD for a while and actually wrote some software to track where COVID was appearing and also what treatments were working and what weren't. And so this was a massive big data collection problem, and he helped with that in the sort of urgent first few months of COVID all hitting. After his PhD, he went to UK and he was optimizing the UK energy grid for clean energy, and now he's back in Australia and he's designing a space telescope. So anyway, there's all sorts of things that you can do. We tend to take our telescopes and point them up at space, but you can also take space telescopes and point them down at Earth, and that can be really important for things like fire and crops and forestry management and floods, etc. And I was talking to a bunch of the Queensland space industry people who really, really were begging me for more astrophysics graduates so that they could go and help them out with their commercial projects looking at the Earth from space. Okay, so that I'm going to take us back to this nice, relaxing picture of a tree. We've looked out and looked at the universe and seen that there's a lot of cool stuff out there, and this dark energy, dark matter stuff is a little bit mysterious. But a couple of 100 years ago, we didn't know what air was made of, right? We didn't have a periodic table. We didn't have the particle theory of matter that we have these days. I'm wondering what we're going to be able to do 200 years from now, once we've figured out the periodic table of dark matter or something like that. Who knows, but I'm excited to find out. Thanks very much. So I think we have some time for questions, is that right? Yeah. Does anyone have any questions? There's one eager right up the back. We do know why that is. Here's one I prepared earlier moment, literally my next slide. So where that repeating pattern that we see isn't random, and we know it was predicted to be there before we ever saw it, and the prediction matched beautifully when we were able to measure it. And now what we think happened was that there was a whole bunch of density fluctuations in the very beginning of the universe, just after whatever caused the bang to bang. And if you have a dense spot, a dense spot here that's slightly denser than its neighbours, then that should propagate as a sound wave. So it would propagate as a sound wave, and it actually propagates at over half the speed of light. And so what you end up with is dark matter in the centre that hasn't moved, and normal matter that's moved as a sound wave. And you end up with like an overlapping sort of, set of sound waves. It's all like messy and stuff, but on average, there's this, at some point, the universe got so dilute that sound couldn't travel anymore. And at that point, it was like freezing the ocean. It's like the sound waves just got frozen in place. And the places that were denser is where gravity pulls in harder, and that's where galaxies formed. So the characteristic distance, the distance that sound could travel from the beginning of the universe until the point where sound couldn't travel anymore, that leaves a characteristic length in the separation of galaxies that we can measure today, and that's the grid paper that we use to measure the expansion of the universe. Does that make sense?
So it's like the speed limit of sound?
Yeah, it's the speed of sound, which we can calculate because it's actually just really easy thermodynamics. It's like you can do it in undergrad, no worries. Because there wasn't even any molecules back then. There was basically just hydrogen and helium and light. And you just had a plasma of that, and the calculations for what goes on there are actually really simple. And so they predicted what you would expect to see, and we saw exactly the pattern that was predicted.
Thank you.
Welcome.
Thanks very much for the lecture. Great visuals. I saw some preliminary results from DESI, Dark Energy Survey. You probably know heaps about it, but they were talking about the fact that to fit their data, it looks like the cosmological constant is actually reducing, and about 11 billion years, I say billion, not million, 11 billion years, it should, from their data, it looks like it could go to zero and actually reverse, and the actual, I guess, timeline of the universe looks like about 33 billion years, ending in the big bounce. That's what fits their data so far. Do you have any comment on that?
Yeah, so that's actually the data that I was just showing you. So that DESI data is exactly that result that you're talking about, that it's getting the dark energy could be weakening with time. But it wasn't just, so that was the stuff that we got from here, but it wasn't just from there, it was also from the supernovae. So this bit where I say that we measured the changing properties of dark energy, this is dark energy weakening. So we measured it both with the supernovae and with the galaxies. And it's not a super significant measurement yet. We need to get more data to be sure that it's actually happening. At the moment, it still could just be a bit of an accident or a fluke in the data. It could be a statistical fluctuation or maybe a slight systematic error or something, because it is pretty subtle. What you're talking about with it changing and then, so decaying and then flipping sign, basically, so it becomes attractive again, is probably an over-extrapolation that we can't quite justify yet. Because the model that we're fitting to see this is a linear model, so it's just a straight line. But there's no real good model that would expect it to just keep traveling in a straight line. It would usually have some sort of shape. It might asymptote to zero, or it might do something else. So the fact that all that we can say at this stage is that it seems to be changing, maybe. Exactly the form of that change needs a lot more data to be able to understand what's causing the change before we can really say anything about what will happen in the future on that.
Probably got time for 2 more questions.
Any kids want to ask any questions? Oh. There's one down here.
Thank you. You were saying if it turns out that the acceleration of the universe is slowing over time, the dark energy is weaker over time, doesn't that undermine the argument that the intrinsic energy of empty space is the main driver? Because as space gets bigger, there's more of it, and that therefore should theoretically accelerate, right? Or
Yeah.
be stronger.
So the standard theory is that if it is just the energy of the vacuum, then as the universe gets bigger, you essentially get more vacuum, right? Because there's more empty space. And so that's what we thought we had been seeing. And indeed, if you looked really subtly at my little acceleration picture here, you might have noticed that in the bottom here, I have it decelerating initially and then accelerating. And that's because the early part of the universe was dense enough that the matter pulling in was stronger than the dark energy pushing out. And we've been able to measure that, so we see that in the past. And people had already done that before we saw any time-varying dark energy. This is actually measuring the jerk of the universe, this part. So it was done before our results. And so the fact that this sort of is concave in and then goes out would be the deceleration and acceleration of the universe. So what we're seeing is that the amount of acceleration we're getting now is not as much as we would have expected given the amount of extra vacuum that we can see. And so that's the kind of thing that we're seeing it could be weakening. So yes, to answer your question, if our result turns out to be true after we get a lot more data to confirm whether it's there, then that would mean that just a plain old cosmological constant, plain old vacuum energy is no longer a really good fit to what our data is. Yeah, so it could be, or it could be something even more sinister. So there's a possibility that our vacuum could decay. Now that's a really bad idea if that happens. So because we do actually think that there was a period of the universe that had a really rapid acceleration in the past, and that was just right basically at the Big Bang. There's a period we think called inflation where there was an accelerated expansion, we think, and then that turned off for some reason. And when it did, it dumped a whole bunch of particles into our universe and basically gave birth to all of the hydrogen, helium, and stuff like that. The energy that had been pushing out was dumped into particles. And so if our acceleration turns off, we would be potentially bathed in a sea of new particles and radiation that would definitely fry us. Anyway, so on that cheery note, no, so there's a whole bunch of different options. It's just opened a can of worms, basically, saying that maybe it isn't just the vacuum energy.
Yeah, thank you. I just had a question about Cepheid variables, because for supernovae you said they get very, very bright. Do Cepheids also get as bright? And if not, why aren't we using them anymore?
We still use them, but for the Cepheid variables, you have to see the individual star, and you can only do it in nearby galaxies, because when you look at the distant galaxies in these pictures that I was showing at the beginning, so if you look at like the distant galaxies here, there is no way that you can see an individual star in this image, right? But you can still see supernovae because the supernovae outshine the galaxy that they're in. So since they outshine the host galaxy, you can see supernovae in these, but there's no way you could see a single star. And that's why we can't use Cepheids apart from the sort of very nearby universe. Yeah. Okay, we might have one last, or did you have a question up there, or one last question down here maybe? Oh, and one up here? Yeah, should we jump up here first and then we'll come down here?
Not knowing anything about astronomy or astrophysics, one of the things that struck me when I was looking at the images is that it looks like a lot of medical images. It looks like mammograms and medical imaging and brain cells and things. So is the pattern of the universe replicated inside ourselves and we're all just part of the same kind of pattern?
It's a great question, and indeed, like one of the other spin-offs that we do is like a bunch of people from astronomy go into medical imaging, and the digital cameras and stuff that we develop can go into medical imaging. And another one of my colleagues is looking at has made an app on your phone that's hopefully coming out soon, where you take pictures of potential skin cancers, and you're able to see if they change over time using the same software that we use to see if supernovae change with time. But to answer your question, there are certain patterns that do repeat on different scales in the universe. And so you see things like our moon is orbiting the Earth, and like you look at Jupiter and the moons are orbiting Jupiter, or you see Saturn and there's the rings of Saturn. And then we've got our sun, and all the planets are in a disk around our sun. And then you see our galaxy, and all of the stars are in a disk around the black hole. And so you've got the same sorts of patterns happening on different scales. And in that particular case, they all come from the same kind of process. When you have something that collapses under gravity and you have the friction of particles bouncing on each other, they tend to form disks. So on whatever scale you're doing it on, you get a self-similar sort of pattern. So exactly how it works with compared to cells in our body, I don't see quite as clear an analogy right there, but it's all physics when you come down to it. And so you see these patterns emerging in similar ways in different places. Yeah, and one of the really cool questions that we want to ask with James Webb and some of the other stuff, and people like Ben Pope in the audience here are looking at some of these things, is whether there's life on other planets, and whether we can see exoplanets, like planets that orbit other stars than our sun, which we know of thousands now, but yeah.
Yeah, thanks, Tamara. It's all fascinating stuff. When I went to school, which is many decades ago, I learned, or I was taught, that a vacuum was empty. It's not the case anymore. Krauss, in his book, A Universe from Nothing, actually says a vacuum isn't empty anymore. And he says nothing isn't nothing anymore, famously. I know a little bit about fields and stuff and how we describe what goes on in a vacuum. But have there been any recent advances in our understanding of what the vacuum actually is? I mean, you said it decays or it does this or that. Do we have anything other than a mathematical model of what we think the vacuum is?
Yeah, so it's a really fascinating question, and it's a really, really cool aspect of quantum physics that says, actually, you can't have anything completely empty. How many people have heard of the Heisenberg uncertainty principle? Oh, look at so many. Oh, what a great audience. So the Heisenberg uncertainty principle says you can't know both the position and momentum of something perfectly, right? And if you do a bit of a transformation of coordinates, it also says you can't know the energy and duration of something perfectly. And that means when it comes to quantum physics, you sort of can't know that there's nothing there. Like, so you can sort of borrow energy from the universe from nothing as long as you do it for a short enough amount of time. And so what we think happens in the vacuum is these particles basically pop in and out of existence, and a particle-antiparticle pair will appear, and then they'll annihilate each other. And so the vacuum, we think, is a seething froth of like stuff happening. And some of the evidence that we have that this actually happens is something called the Casimir effect, where people took a couple of plates in almost vacuum, and if you put two pieces of metal together, the kinds of particles that you can make inside, you can only make stuff that has a wavelength shorter than your separation. And so you end up with a higher pressure of vacuum on the outside than on the inside, and it pushes the plates together. So there's some controversy over that, but that's one of the pieces of evidence that we think that these virtual particles happen. And one of the these virtual particles are often, or are also one of the potentially limiting factors in keeping quantum computers stable and isolating single particles. And so this is a really important part of physics to understand better. And it's cool that it exists like this. And maybe it has something to do with what the dark energy is. And we just haven't quite figured out how to merge quantum physics and gravity yet in order to be able to understand that well enough.
Could gravity be a Casimir effect?
No, gravity can't be a Casimir effect, I don't think, but it can, when you borrow energy from the universe, or what we think the vacuum has is a negative pressure. And usually when a positive pressure is when stuff moves around really fast and bounces off itself. Like if you have particles that have energy, they push out, they have pressure. But weirdly, a positive pressure in the universe actually gravitates, because positive pressure can only do work if you've got high pressure here and low pressure over there. Then it can push a piston. But if you have high pressure everywhere, it can't push anything anywhere. The only effect it has is because it has particles moving around with high energy, energy gravitates. And so high pressure actually decelerates the universe more. And this vacuum has negative pressure, and that's the thing that pushes. That was a more technical answer that I probably should have gotten into, but anyway, yes, thank you very much.
Thank you all for being here to celebrate the 25th Moyal Medal lecture and presentation. And let's thank Tamara one more time, sorry, for a fantastic talk.
Thanks very much.
light doesn't.